So 4, 3 beta. We're going to start with example 3. In example 3, there's a picture in your book. I'm on page 208 of e to the negative x squared. Here's the picture of the graph. And this is really interesting because this is connecting calculus and statistics, and e raised to the negative x squared is the parent graph of the standard normal curve. We have to do a transformation to this graph to get the standard normal curve. We're going to go over that. If you're not in statistics yet, then this won't apply as much to you. You're not going to have to do the transformation for our course. But it says, find all points of inflection. So what are we going to do? We're looking for the critical values. We want to set the second derivative equal to 0. If you have point of inflection, then the second derivative is 0 or fails to exist. But, converse error, if the second derivative is 0 or fails to exist, you do not necessarily have a point of inflection. You have to confirm the sign change. And that's what College Board is going to be. Those are the type of questions you're going to get in the spring to see, test your depth of this knowledge. So, what happened here? You essentially have e to the mu. So the derivative of e to the mu is itself times d mu. And here's the first derivative. In the middle of the bottom page 208. For the second derivative, we need to use a product rule. How do they do this? We said the derivative of the first term is itself times d mu times the second factor, plus the first term times the derivative of the second factor. And you have this addition symbol here. So they factored out the greatest common factor of both sides of the addition symbol, which is e to the negative x squared. Multiply these two together, and you would have this times 4x squared plus a negative 2. And you want to set that equal to 0. Well, you cannot raise e to any power and get a 0. So I'm only worried about that quadratic in there. So to set that equal to 0 with second degree, we'll have 2 zeros. How many are real? 2 or none. And they're both real, and it would be the positive and negative square root of 1/2. So we look here, we take this information into an H chart. We have x, we have y. We have dy dx, and we have the second derivative. What does that mean? The second derivative is 0. At the opposite of the square root of 1/2 and at the square root of 1/2. Now, the square root of 1/2, right, is 1 over root 2. You can rationalize and get root 2 over 2. It's the same thing. I wouldn't really be worried about rewriting that as root 2 over 2. It's the same value. Okay? Need confirmation, you go to the calculator. The square root of 1/2 And the square root of 2 divided by 2. There's two ways of writing the same thing. Okay? So now what? Well, we want to confirm what's going on in here. We have a size change. So we have to go to values to the left in here and to the right. The square root of 1/2, which we saw was 7/10. So we could go to -1, 0, and 1. Make sense? So the derivative, all we really care about, well, let's put the whole thing. So we go over here and we say, go to y equals, and I'm going to type the question. Second ln, which was e to the negative x squared times 4x squared subtract 2. This is the second derivative of the parent graph. So I'm going to start at -8/10 because I saw what the value was last time, and make the delta table 1/10. Understand what we're doing here? We saw that this is approximate, this is a number a little greater than -8/10. Right. We're looking for a sign change in the second derivative. What happens? Well, we see it here. 8/10, -8/10, this number is positive. The graph is concave up. At this value, the second derivative is negative. On the second derivative is 0. So there's a potential point of inflection. But we have to confirm that by going to another point. At -7/10, it's negative. Or you go to 0 if you want. It's negative. So you have a sign change here. The sign change is confirming you have a point of inflection. And if I scroll down, you saw the graph symmetric. Well, the same thing's happening here. When you get past the square root of 1/2, it's positive again. What's that telling you? To the left of this value, the graph is concave up. Between these values, the graph is concave down. And to the right of the square root of 1/2, it's concave up again. So we're talking about this table confirming what you saw in the picture. So if you had to do this work without a calculator, you wouldn't have to see the picture. Make sense? This graph is not going to change in copy again. Fundamental theorem of algebra. There's no more zeros. There's no other chance for this graph to change in cavity. So if I go here, and you see this picture, here's the graph opening up. Then it begins to open down. And where this cursor is in quadrant 1, this is a decimal approximation of the square root of 1/2. That's when the second derivative was 0. That's a point of inflection. And that's when this graph starts to stops opening down and begins to open up. And then you can see, they didn't show you both of them, all you do is reflect that into the second quadrant. Make sense? The most important part of this is the H chart. You need to understand how to use them. If you have a critical point, whether it's for the first derivative being 0 or failed to exist, or the second derivative being 0 or failed to exist, you need to confirm the sign change. College Board's all over that. They'll give you critical points where there's no sign change, and then that choice, that answer would be choice A. If you don't read the rest of the choices, read B, C, and D, because they found what they were looking for, but they didn't consider the converse of it. So, this is your model. Here's the work. You're going to problem number 13, please. Okay, so before we get to 13, I just want to point this out to you. You saw in example 3 that the inflection points occur at the square root of 1.5 and the opposite of that. Another way to write that is root 2 over 2. To get to the standard normal curve, which only really interests the people in statistics right now, this is the magnitude of your scale change. So if you do this scale change to this example 3 parent graph, y equals e to the negative x squared, by doing the opposite. Divide x by root 2, divide y by 1 over the square root of 2 pi. It does two things. It moves the inflection points to -1 and 1, and makes the area under the curve 1. So, 13. Here is the graph, and get the derivative. We use the product rule. To get the second derivative. The derivative sum is the sum of the derivatives and the product rule, which you just did up here. Because this, derivative of this is itself, the derivative of this is what you just did. And the greatest common factor is e to the x. When you factor it out, you get this x, and then 1 and 1, which adds up to 2. So what happens? You have at -2. At -2, the second derivative is 0. At -2, the function is this. So in my table, at -2, the second derivative is 0. There is a confirmation of sign change, so you have a point of inflection. So I went to this in y1, and I typed the second derivative, and I went to the left of -2, and typed in -2.1. I went to the right of it, and typed -1.9. So the graph was concave down, came to a point of inflection, and began to go concave up. The next thing is a picture. Now, the picture is very important. Oh, it's a picture. It's not like kindergarten when you saw picture books. These pictures are important. You have to be able to interpret the picture. So I'm looking at example 4. This is a picture of the derivative. That's f prime of x. And it asks you, when is the parent graph increasing? Well, the parent graph is increasing when the derivative is above the x-axis. Yes, we know that. That's a pretty user-friendly question, okay? From -4 to 1. When is the parent graph concave up? You got to think about this. So in order to do that, I got to think about the derivative of this picture, because this is the first derivative. So what would the second derivative look like? And for the second derivative, for the parent graph to be concave up, the second derivative has to be positive. So how can I tell when the second derivative is positive? When the first derivative is increasing. And it's increasing between -2 and 0 and between 3 and 4. So question B takes a lot more thought than you would assume. You have to say, that's the picture of the first derivative. What would the derivative of that look like in order to answer that question? Then C asks, what are the local extrema? Well, here you have a critical point. The first derivative is 0, but there's no sign change. To the left of that 0, it's positive. To the right of that 0, it's positive. That was a critical point. It did not give you a local max or local min. Here's a critical point. At 1, what's happening? The derivative is positive and then negative. So this is a local max. The parent graph is going up, and then it's going down. That's how it behaves around a local max. Okay? And then we're saying the minimum. Think about this. The min is what? Positive and negative. Well, ready? 4 is a local min. Because the graph is decreasing to get to 4. Makes sense? Because the derivative is negative. What about -4? It has this value, -4, and the derivative is positive. So it's increasing away from -4. So that's also a min. Points of inflection. Where are the points of inflection? I got to think about, what does the picture of this look like? What does the picture of this derivative look like? You've got on the first derivative, you've got a local min, a local max, a local min, which is saying that you have a sign change there with the derivative of that. So there is way more to this than just looking at a picture. Like question A, when's it going up? Yeah, we've done that, beat that into the ground. But B through D is heavier lifting. Right? So you're going to go to, now in the book, they do this on page 209. They drew, the parent graph could look like this. Does that make sense? Why would they say it could look like that? Because you could have a slide of this graph. It doesn't affect the shape. You can slide this graph that they drew up, you can slide it down. It would still have the same shape, same slope. So they said that's an example of what the parent graph would look like. It's back to the Pringles, where they sit in the can. So if this is the Pringle in the middle of the can, the Pringle below it, the Pringle above it still have the same shape. Okay? So that's your model. You're going to problem 23. Okay, 23. Here's the picture. So when is the parent graph? This is the derivative. When is the parent graph increasing? No, what? These two are. Ready? General notation. Infinity always gets parentheses. This bracket at -2 is just telling you the function's continuous there. So you say, well, you got -2 bracket, it's increasing. Down here you have -2 bracket, it's decreasing. It's not doing both at -2. That bracket's telling you that the function is continuous. So here's where it is decreasing. The local max. It's increasing, begins to decrease. Increasing begins to decrease. Local min, decreasing begins to increase. So there was more content in the example than in the exercise. But you are accountable for what was in the example. Okay? So that is the beta lesson.